So we're going to take a look at the first derivative test for local extreme values. But first, I want us to examine this figure, and I encourage you to pause it and think about what this is saying. So between A and C sub 1, we have a positive derivative, and if you'll notice, everywhere between there, the tangent line slope would be increasing. At the point C sub 1, the derivative is equal to 0, and you'll notice there is no extreme value there. We have actually a saddle point. This is actually a point of inflection, which we talk about a little bit more in the next few videos that we'll see. All right, between C sub 1 and C sub 2, the derivative is still positive. So you'll notice any tangent line I would draw in between here would have a positive slope. And at C sub 2, the derivative is equal to 0. We have a horizontal tangent line that represents a max. All right, so if you look at my first interval, the derivative was positive. My second interval, the derivative was positive. And if you look at my third interval, you can see that the derivative is negative. So the derivative changed sign. We went from positive to negative, and we had a max. So between C sub 2 and C sub 3, we had the derivative is negative. We end up with a decreasing function. And between C sub 3 and C sub 4, the derivative is positive, which gives us an increasing function. And so you'll notice here that we changed from negative derivative to a positive derivative, which indicates we had this turning point, and we had a local min right in the middle where the derivative was equal to 0 at C sub 3. Okay, so we're paying attention to whether or not the derivative is positive, negative, or 0. On my next interval from C sub 4 to C sub 5, the derivative is negative, so we are decreasing there. And you'll notice we have a sharp cusp. That's because this is not differentiable. The derivative is undefined. We can't take the derivative. It does represent the highest point on the graph when we consider the entire graph from A to B. So it's the absolute max. But it's a sharp curve, a sharp point, which is not differentiable. And again, the derivative is undefined. At C sub 5, down here, we end up with another saddle. We do have a change in concavity. We talk about that moving forward. But the derivative is equal to 0. That's actually a point of inflection. And then lastly, from C5 to B, on this very last interval here, all of my derivatives are negative, so it is decreasing. Okay, so pause the video, think about this, understand what's going on, because we're going to start using the derivative to make decisions about the function. And I've pulled another screenshot from our book in. We have a first derivative test for local extreme values. So if we have a critical point of a continuous function, and that function is differentiable everywhere in some interval which contains C, except possibly at C itself, as we move across the interval from left to right. So we noticed this when we were looking at the graph. If my derivative changes from negative decreasing to positive, What we know is we have a local min. If f changes from positive to negative, we would have a local max. And if the sign does not change, so positive on both sides of that critical number or negative on both sides, it does not represent an extreme value. So this is just one more piece of knowledge we use to infer and make decisions about our function's behavior. So let's do another example. So we're going to consider this function f of x equals sine squared x minus sine x minus 1 on the closed interval between 0 and 2 pi. So we want to identify any intervals where the function is increasing or decreasing and any extreme values. So in order for us to do this, the first thing we do is we take the derivative and we set it equal to 0. Taking the derivative and setting it equal to 0 is going to give us our critical numbers. So you should pause the video, make sure you can take the derivative of this function and solve it equal to 0. I'm going to pause and work it out. So my first derivative here is 2 sine x cosine x minus cosine x. The derivative of sine squared, well, that becomes 2 sine x to the first power, but then we have to take the derivative of the inside, so the derivative of sine is cosine. That's our chain rule. And then the derivative of sine x, that becomes minus cosine. The derivative of 1 is 0. So if I set this function equal to 0 to solve and find my critical numbers, setting it equal to 0, I'm going to factor. And in this case, I can factor out a cosine x. Factoring out cosine leaves me with 2 sine x minus 1. And if I set this equal to 0, I'll be setting 2 factors equal to 0. I'm solving cosine x equal to 0. And this, if I add 1 and divide by 2, I'll be solving sine x equal to positive 1/2. So we have to say, well, where is cosine x 0? This takes us back to our unit circle logic. Where is x 0 on my unit circle? And that's going to be at pi multiples of pi over 2. Okay, so pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, or in the opposite direction, negative pi over 2, negative 3 pi over 2. And then we also say, well, where is sine equal to 1/2? So where are my 1/2s going to show up on my unit circle? And that happens at pi over 6. So we've got pi over 6, and sine is positive in the first quadrant, and then also in the second quadrant. So my pi over 6 in the second quadrant is 5 pi over 6. And we could say plus pi k on each of those. But in actuality, we don't really need pi k at all, because we're talking about this only within one revolution of the unit circle. So I'm just going to go ahead and list pi over 2 and 3 pi over 2. So these are my critical numbers. I have 4 critical numbers. So I take those critical numbers, my critical points, critical values, whatever you choose to call them, and we're going to plot them on a number line. And so my number line, we're only dealing with 0. The first value would be pi over 6, and then pi over 2, 5 pi over 6, and 3 pi over 2. And so I'm using the endpoints here, 0 and 2 pi, because we're on that closed interval. So we're looking at everything that happens inside this interval. All right? And when we talked about absolute max and absolute min, we always used those endpoints. So I'm going to bring in a picture. So I've brought in this picture. I've got my critical numbers plotted on my number line, pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2 in ascending order. And then we're going from 0 to 2 pi, and we don't want to go past 2 pi in this situation. Okay? And so what we said in our last example was that we would pick a test value on each interval. We can test any number we want. And it might help you to think about degrees and using your calculator in degree mode. Pi over 6 is 30 degrees. Okay, whatever works for you. But so you'd be testing a value on each interval. You can pick any number you want. But what we're going to notice here is that when we plug the test value, whichever number we choose in between each of these radian values, from 0 to pi over 6, I get a negative value. From pi over 6 to pi over 2, I get a positive value. And I really don't like the way this table looks now that I'm looking at it. We've got negative, positive. That just looks messy. Between pi over 2 and 5 pi over 6, we get a negative value. From 5 pi over 6 to pi over 2, we get a positive value. And then from 3 pi over 2 to 2 pi, any number we choose on that interval would give us a negative value. So you should see a correlation. Wherever I decided the derivative was negative, we have a decreasing interval. And wherever the derivative is positive, we get an increasing interval. Okay? If we want to state where the function is increasing or decreasing, it is decreasing on any interval where the derivative is negative. So we're decreasing from 0 to pi over 6, union pi over 2 to 5 pi over 6, union 3 pi over 2 to 2 pi. And we are increasing when x is in the set pi over 6 to pi over 2, union 5 pi over 6 to 3 pi over 2. Okay? So increasing and decreasing. And again, just to remind you, when I was determining my positive and negative values, I determined them by picking a test value, a random number on each interval in between each of those, and I plugged them in to my derivative. You have to plug them into f prime of x, and we're looking to see if the derivative is positive or negative. And I encourage you, again, pause it, make sure you can do this on your own. So the last thing we want to talk about here is, are there any extreme values? So I'm going to zone in just on this number line here. All right, and we said we had negative, positive, negative, positive, negative derivative values. So negative means that the graph is decreasing. So I'm going to have a graph going down on all of those. And positive indicates that the graph is increasing. So what you notice, if we change from decreasing to increasing, what is going to occur? And what we see is, because we went down and then up, we knew there must be a minimum value. There's a minimum at pi over 6. Where else is there a minimum? At 5 pi over 6. Where else is there a minimum? That's it. So we know there are local mins at both of those x values, and we could write them as ordered pairs, pi over 6 and 5 pi over 6, and we could get the y value by plugging it into the original function. Furthermore, we have some maximums, and the maximums occur when we have a positive derivative that turns around and becomes negative. So positive to negative, there's a max at pi over 2, and then we also change from positive to negative at 3 pi over 2. So this allows me to develop some ordered pairs. And if I want the y value, if I want to say these ordered pairs, right, because the max or min is y at some x value, right? If we want those values, we're going to plug them into the original function. You don't want to plug them into the derivative because these are all my critical points. They came from the derivative being equal to 0. So you want to plug them into the function to get those output values. And I've come over to this next page here, and I've pulled up a picture of the graph of the original function. And you see there's a min at pi over 6, and there's a min at 5 pi over 6. And there's a max at pi over 2, and a max occurs at 3 pi over 2, right? And just as we said, decreasing, increasing, decreasing, increasing, decreasing.